So there are a couple of different ways to solving this problem. One of them that I posted before is just using algebra, and that is actually a much clever way to solve this than using calculus. But let me tell you how to solve also this problem using calculus. Again, the problem is that we have x to the fourth plus 3x cubed. There is some line that is tangent at 2 points, and we want to find the equation of that line. The approach using calculus is also based on the same idea that we used in the algebra way of solving this problem, which is that we're going to start from the function x to the fourth plus 3x cubed, subtract the tangent at some point x equals alpha, and then look at that difference. As in the graph, what we want is that tangent, we want to find the tangent, the point alpha, such that the tangent is tangent at some other point. At that point, the graph will look like in green here. The function, the difference, will have a double zero. Here we go. So this is the function we're interested in, and this is the general equation of a tangent line at a point x equals alpha. If we specialize for that function f, this is the equation of the tangent line. Now, what we want is the difference of the function minus its tangent line to have not only one double root, this is the tangent line, so the difference has to have a double root at x equals alpha, but we want it to have two double roots. We want to have a second double root beta that is going to be telling me that there is another point where this line is tangent to the graph. Now, how do we factor this to see if there is a second double root? What are all the roots of this polynomial of degree 4? That seems complicated, but calculus is going to help us factor this. What I'm going to do is actually write the Taylor expansion of f of x at x equals alpha. This is a polynomial, so its Taylor expansion will be actually finite, and it will equal this. So we start with the Taylor expansion, the constant term, the first derivative times x minus alpha, etc. And then we actually don't have to go beyond the fourth derivative because this is already a polynomial of degree 4, and that's a polynomial of degree 4. So this has to be an equality of polynomials. And notice that the first two terms, the constant term and the linear term, are actually the tangent line. So when I subtract from this, the tangent line, what I'm going to get is this, these three terms together. So what I now need is for those last three terms of the Taylor expansion to have a double root at alpha and some other double root. So if I factor that, actually it has an x to x minus alpha a square factor, which tells me that, of course, alpha is a double root already. And then I get a quadratic expression in alpha. And this quadratic expression is what I want it to be, x minus beta squared, that it has one repeated root. That polynomial will have a repeated root if its discriminant, b squared minus 4ac, is 0. And if I find that polynomial, that is this polynomial, and this will be 0 when alpha is exactly minus 3 plus 3 square root of 3 over 4. And now that I know that alpha is minus 3 plus 3 square root of 3 over 4, this is one of the coordinates, one of the x coordinates of one of the tangent points. And since I know that the line is given by this equation, I can plug in this number into these coefficients and find out that the tangent line is 27 over 8x minus 81 over 64, and that is the solution to the problem.